about Turing machines and sort of where they fit in um, as far as the hierarchy of languages. Remember, we all along, every so often I draw sort of a blobby diagram like this. There's the regular languages, which is like A to the N. There's the context-free languages, which is like A to the N, B to the N. And then there's a larger category outside, including things like A to the N, B to the N, C to the N, which is not context-free. But we know you can make a Turing machine that accepts A to the N, B to the N, C to the N by marking stuff. We did this example in class. It's not so difficult if you're comfortable with the marking Turing machines. So actually, there's a name for this category. In fact, there are sort of two larger categories that involve Turing machines. And this one is in, well, let me just, how about this? I'll draw the two blobby blobs. There's two more categories which we are going to give names to today. Actually, sorry, there's sort of, I'll draw yet another one. I'm not going to give names to all of these things today, but these are the categories that I want to talk about. The one for this first dot with the question mark, this category here, I'm going to tell you the names of both of these, but the inner one, A to the N, B to the N, C to the N, that one is a little harder to describe. But anyway, here's a first definition. Maybe I should have waited to draw this diagram until after I gave you the definitions. A language is called... I want to give a name for the category of languages which can be accepted by a Turing machine, right? That name, unfortunately, isn't like Turing languages or something like that. That would seem appropriate to me. But anyway, it's called, so I'm going to say a language L is called, so the word here is recursively enumerable. Recursively enumerable, and we are going to say RE typically, just because it's a pain to write recursively enumerable, if L is the language of some machine for some Turing machine M. Is that too many abbreviations? For some Turing machine M, if L is the language accepted by the Turing machine, then it's called recursively enumerable, all right? RE means that you can make a Turing machine which accepts this particular language. And on the diagram, that's actually this category right here is the REs. Now, that includes all of the lower categories, so it does include things like A to the N, B to the N, C to the N, but actually A to the N, B to the N, C to the N is in a special category which is smaller than the RE category, which I will try and describe, in 10 minutes or so. We'll come back to that picture. But anyway, RE means it is the language accepted by a Turing machine. The reason for these two separate categories, and I haven't given a name yet to the inner one, is there is a bit of a subtlety about Turing machines. Turing machines have special categories of non-accepted strings. And I don't know if anybody ever noticed this. Actually, one person on your test, on the Turing machine question, wrote something, gave a weird Turing machine, which was not a correct answer to the question. It was so weird, actually, that it displayed some of the behavior that I'm about to describe here. Special categories of non-accepted strings. So sometimes a string is not accepted because the machine stops because it doesn't have an appropriate arrow, and that's usually what we see on the Turing machines that we've done. So I will say a Turing machine can halt and reject some string. This happens if there's just no outgoing arrow from the state that it's in when it tries to read the next appropriate letter. So a Turing machine can halt and reject a string when there's no appropriate transition, or I'll just say arrow. All right? We say in that case it halts and rejects the string, but, and that's when I say reject. So actually on a Turing machine there are accepted strings, there are rejected strings, but then there's a third category, which is not possible on the DFA or any of the other ones we've talked about. Also, this is a third category. A Turing machine can run forever for certain inputs. And I will try to give you an example. And this is actually somebody came up with an example of this with your bogus test answer, which I thought was kind of interesting, although you didn't get any credit for it. No extra credit, at least. Here is a Turing machine. This is not the same one that somebody put on the test, but this is a simplified version, which does what I'm trying to talk about here. How about this? All right, here is a simple Turing machine. So you can see, first of all, what kinds of strings are accepted? The answer is anything that starts with a B will be accepted in this Turing machine. What if it starts with an A? So what about AB? Is this accepted or rejected? I'm going to try to draw the kind of the step-by-step, right? So we begin with, my states are called 1 and 2. We begin like this. We're in state 1, and it's pointed at the A. And then I read the A. I should be following this arrow up here, up top. Move to the right, keep the A like it is, and go to state 2. So my next thing should look like that, right? Keep the A like it is, move to the right, and switch to state 2. Now in state 2, I read a B, which means I keep the B like it is, move to the left, and change to state 1. So what that does is this, 1AB, right? Anybody see where I'm going with this? What's going to happen if we continue? Yeah, it's just going to bounce back and forth. On the head, on the tape, it will move back and forth, right and then left. And in the diagram of the states, it'll go back and forth from 1 to 2. But this will never halt, and it will never accept, right? So the next state is, the next state will be A2B again, etc. This is really going to run forever, all right? And would you believe me if I said, actually, this is not only, this kind of weird behavior is not only for the string AB. In this example, anything which started with AB would have the same behavior. Even if there was more stuff after the B, it would never even make it to that stuff. So in this example, so I will say this Turing machine loops on any string starting with AB, right? If you have AB followed by any other stuff, it's going to run forever. It will never halt and reject, and it also will never accept, all right? If it starts with a B, remember, if it starts with a B, it's immediately accepted. And if it starts with an A, but then is followed by another A, then it will be rejected, halting, all right? So actually, we can say completely what the three scenarios are. In this particular example, this Turing machine, it accepts anything like BX, right? If it starts with a B and then has anything, it will be accepted. It rejects anything like AAX. If it has an A followed by another A, it will actually halt and reject, right? And it will loop forever on inputs like ABX. And that actually covers all possibilities, right? If it starts with a B, it accepts If it starts with the A, and then another A, it rejects. If it starts with the A and then a B, it loops forever. And I got this line somewhere. All right. So there are three categories for a Turing machine. That's what I'm trying to say here. And we have notations for all of those. Okay, so the set of accepted strings is what we write as L of M, as usual. L of M means the language of the Turing machine, that is the strings which are accepted. The other two, we have names for those. So the rejected strings, these are rejected and halting. Those are written R of M, R for reject, I guess. Which, and in this example, we can say exactly what these are. The accepted language here is BX. The rejected language is AAX. And then there's the looping strings. And this is written as F. I would have said L, but L is taken already. F, I imagine, is for forever. I don't know. Anyway, F of M is, in this example, ABX. Right? A Turing machine has three categories. It can either halt accepting, halt rejecting, or it can loop forever. All right? Now, as far as a real-world machine that you would want to do computations, it would be preferable if you knew that the machine never had any looping strings, all right? In terms of a real machine that's supposed to do something, you would like for that machine to either succeed in what it's doing and stop, or maybe fail in what it's doing and stop. You don't want it to run forever and never produce an answer, because then you, as a user, you can't tell the difference between if it's running forever just because it didn't figure it out yet, or maybe it really is running forever and it's never going to stop. Right? This is bad in the world of real machines. So I would say, ideally, in terms of actual useful computing devices, we would like for F of M to be the empty set, right? As far as a useful computing device, we don't want it to have certain inputs where it runs forever. We would like it to either give me the answer, or at least, if you're not going to give me the answer, stop and say, I'm not going to give you the answer. Don't keep me waiting, and then I don't know if you're just taking a long time, or if you're really going to take forever. All right. So ideally, in the real world, we would like for our Turing machine to have no strings for which it loops forever, and there's a name for that. So the definition of that, if M, I'm going to say, always halts, i.e., F of M is the empty set. That is, there are no strings for which the machine loops forever. It either accepts or rejects by halting after a finite number of steps. If M always halts, then it is called a total Turing machine. Total. A total Turing machine is one which never, it has no inputs which can make it loop forever. All right? And this is where that other category of languages comes from. So that other category of languages, kind of in between the ones I said before, those are the ones which are the language of a total Turing machine. So here's another definition. If L is the language of a total Turing machine, then L is called recursive. All right? Recursive is the name of that other category. So I'm going to scroll back up to that picture that I drew at the very beginning and sort of fill in what I had left out, which is this category right here is the category of recursive Turing languages. right here, this A to then, B to then, C to then, those languages are called recursive. Now, I didn't point it out to us at the time, but when you wrote that Turing machine, which does A to then, B to then, C to the n, it actually, that Turing machine does not loop forever on any inputs. You can tell that it does go back and forth a little bit, but every time it goes back and forth, it's changing the tape as it does so. And so it's never going to get locked into a scenario where it just bounces back and forth without changing anything. All right? Those are called the recursive languages. And it's a big topic for the rest of our, the rest of our semester, which is only a week or so. Are there any examples of languages out here, right? So this category here, the REs but not recursive, this would mean that it's a language which can accept, you can make this language on a Turing machine, but that Turing machine would automatically have some inputs for which it loops forever. And it's not possible to make it on a total Turing machine. That would be an example of something which is RE but not recursive. And then there's this even weirder category out here, which would mean languages which are so crazy, you can't possibly make them on any Turing machine. And we will, by the end of the semester, talk about examples of both of these categories. So there are languages in these categories. I'll tell you right now, it's not A to then, B to then, C to then, D to then. That actually is recursive. That's easy to do, but with marking. So the examples are going to be very, very weird. And if you met yourself, the you 1 week in the future, you will know these examples. If you 1 week from the future came back in time to ask you right now, and you said, hey, what are those examples like? They would say, I don't know, or they're too weird to explain just in a few words. So this is I'm giving you a heads up. Those examples are very, very strange, and they cannot be written in anything like A to then, B to then. Like, you can't just write them in a simple way in terms of powers of whatever. All right, they're totally weird, but we're going to get there eventually. All right. We're not actually going to talk about that today. I just wanted to tell you sort of the names of these categories. And I would like one more thing to say about this before I start talking about something else is there is a connection between computable functions, Turing computable functions, and recursive or recursively enumerable languages. It turns out, and this is something we're not really going to talk about, but I might as well say it. There's a theorem that relates what kinds of functions can you compute on a machine is related to what kinds of languages you can compute with the machine. And the connection is this. I will just say it. I'll say f is computable if you have a function. F is computable on a total Turing machine. This turns out to be equivalent. This is true if and only if this language is recursive. So the question of computing a function, you can convert that by it's not terribly difficult, although I don't want to get into it. You can convert a function computation into a question about accepting or rejecting a string. And it turns out that f being computable, the ability to compute the function is equivalent to making a machine which is capable of recognizing a string like that and deciding if it should be accepted or rejected. Those are the same thing. And it goes the other way around. If you have a machine which can decide to accept or reject one of these, then that means that the function is computable on a total Turing machine. That means it's recursive. And then similarly, if it's computable on just any Turing machine, it means that language is RE, recursively enumerable. All right. So that's the connection between computability and the structure of the languages. We're not going to say much more about that. I would like to talk for our remaining 15 minutes and a little bit next week. What about Turing machine variations? The Turing machine, has very specific capabilities, and I would like to think about what happens to the capabilities of the machine if we try to give it more skills. Like, the Turing machine is only capable of looking at one location on the tape, and it can only move one step to the left or one step to the right in each step, right? What if we made the Turing machine a little bit more powerful? Would that allow you to compute different things with it? That's what I want to talk about with Turing machine variations. So, a simple variation is what if we allow the Turing machine, in every step, the Turing machine can move to the right or to the left. In fact, in every step, the Turing machine, the head must move to the right or to the left. What if we wanted to make our Turing machine a little fancier, give it another feature? What if we allow the Turing machine to stay put after a step? So we will allow transitions that look like, X, Y, R or X, Y, L, but maybe we want to also let it just stay put under certain situations. X, Y, S, say. I'll use S for stay, all right? So I'm going to call it a Turing machine that stays, all right? I don't mean it always stays, but sometimes, if you want, it can stay put in one step. And this might be useful for some things. I don't know if any of the examples we've done so far, I'm not sure that really would have been very useful to allow the machine to stay put. Anyway, I would like for us to think about, does this actually make the machine any more powerful? Or do you end up with something that, ends up just doing all the same stuff as the normal Turing machine that we've been talking about so far? Does it really make a difference in terms of what kinds of functions it can compute or what kinds of languages it can accept or reject? The answer is no, it doesn't make much of a difference. So this, I will say, such a machine is actually equivalent to an ordinary Turing machine. How would we demonstrate that? I think it would suffice to explain how could it be if you had a Turing machine that stays put. Could you somehow convert that into a Turing machine that always moves to the left or to the right? So I'm going to try to explain how any Turing machine that stays, this is a simple idea, but I'm going to use some specific terminology here. Any Turing machine that stays can be simulated by a usual Turing machine. All right? That is, if you show me a Turing machine that sometimes stays put, I can show you another Turing machine that never stays put, but does exactly the same computation. All right? And this is called simulating one type of machine using another type of machine. Any Turing machine that stays put sometimes can be simulated by an ordinary Turing machine. How would you do that? So if we see on the machine that stays, if we see something like A to B labeled X, Y with a S, replace this with, let me think, if I have a machine that reads X, puts a Y in the tape, and then stays put until the next step, can you replace this arrow with some things which only use L's and R's but have the same effect? You may have to take more than one step to do it. That's all right. You want to make something that behaves in the same way as this machine, which stays put. Yeah?
We want to do X, Y, and R, and then we want to go back to the left.
Yeah, you should somehow try and break this into two steps where it moves to the right but then just immediately moves back to the left. And then it'll be the same effect as if you stayed put, right? It'll take an extra step, but in terms of what kinds of functions this thing is computing, it will compute the same thing that the other one computed. It'll just cost you an extra nickel if you're paying the nickels. So I would do it something like this. I think he said X, Y, R. So instead of staying put, move to the right by one position, and then go back to the left, no matter what. So here you have to put, I guess, X, X, L, Y, Y, L, etc. No matter what you see in that position, you just move to the left. Even if it were a blank, I will say, how about this? Star, star, L, meaning no matter what you see there, keep it like it is and move back to the left, all right? Then this little, sequence of 3 states here is equivalent to the 2 states above there, all right? And so if you have a Turing machine that sometimes stays put, you can just replace all of the stay put arrows with little things like this, and you will have converted it into a Turing machine that always moves, all right? So this one, I'll say we can convert any S transition like this and obtain a Turing machine that never stays, all right? This is why you will never, again in your life, hear somebody talk about a Turing machine that stays as being anything different from an ordinary Turing machine, because they're a little bit different, but they have the same capabilities, and you could easily convert one to the other if you wanted to. All right, so there's no theoretically speaking, there's no difference between them. All right. What about a Turing machine? Instead of moving one spot at a time, it jumps sometimes. Maybe sometimes it's allowed to move by 2 spots at once. All right. In exactly the same way, you could simulate such a machine by an ordinary Turing machine, which moves 1 step at a time, right? Rather than every time your other machine jumps, say 3 spots to the right, you can easily make an ordinary Turing machine that just does it in 3 steps. So I will say any Turing machine that stays or jumps or has, can I just say, other types of movement? All of these are really, theoretically speaking, equivalent to ordinary Turing machines. There is no benefit in allowing the machine to make other kinds of fancy movements, because any kind of movements that you can imagine like that could be simulated by the ordinary Turing machine anyway. So any Turing machine that stays or jumps or has other types of movement is equivalent to the usual Turing machine. All right? Remember, the general topic that I'm trying to talk about is, what if we make variations to the functionality of the machine? Can we make it do more things that it couldn't do before? Well, if your variation is changing the way in which it moves, you really can't make it do anything better than before, because any other strategy you can think of or abilities in terms of movements, you can simulate them by just, it'll be a little slower, but you can make a Turing machine that just moves 1 step at a time that does the same thing. All right? Another thing you might think about is, what about the tape? The tape itself. How about, here's another sort of whole category of variations. What about if we allowed 2 tapes? How about that? What if we allowed the machine to work with 2 tapes at the same time? So you don't have to try and fit everything into just 1 tape, but you have, 2 tapes to work with, right? So the machine would look like something like this, right? It has this is like tape 1, which the input is written on, A, B, B, A. And then maybe just like in order to help it for during the computation, just to help it out, it gets this other free tape that it can use like as a memory storage or something. This is tape 2, which is not part of the input or anything. It's just an extra tape that you can use to as like a scratch paper, right? And then, this machine would have one head, which is in a particular state over here, I'll say state A, and another head maybe in a different state, state X down here, right? And so the Turing machine has two different heads and two different states. Does this make it any more powerful than the original Turing machine? Certainly seems like the second tape could be useful. Actually, so one way you could use the second tape, actually, we had to go to some great efforts in machines in which they had to split into two branching parallel paths. The two branching paths was necessary if you needed to somehow remember if I had read an A or a B in this earlier step, and you had to use that information later on. You got to branch it out, right? If you had a second tape, actually, that would be a lot easier. You could write whatever letter you wanted to remember, you could just write it into the second tape, and then access the second tape later on. It would be, in terms of efficiency, this would be a helpful improvement. But actually, this also is not a true improvement to the Turing machine. So I'm going to say this can also be simulated. This can also be simulated by a normal Turing machine. All right? And the way to do this, I don't want to get into the details, but basically, you just turn everything into pairs. So this two-tape Turing machine can be converted by making everything into pairs. You would do something like the DFA product construction, and you would turn the whole scenario into something that looks like pairs, A comma blank, B comma blank, B comma blank. So what I'm doing is just the tape 1 and the tape 2, I'm combining them by putting pairs everywhere. And then you also make pairs out of all the states. A comma X, right? Your Turing machine diagram gets much bigger because if you remember the DFA product construction, you get pairs. Making pairs out of everything makes everything much bigger. But I don't want to go through the details, but a two-tape machine can be converted into a one-tape machine by making everything into pairs, all right? So this can also be simulated by a normal Turing machine. So can I just, in conclusion, we got a few more minutes, but I will say adding more tape and movement functionality doesn't change the theoretical capabilities. It does change like the efficiency, the number of steps it takes, that will change, but it doesn't change what it can do in theory. Adding more tape and movement functions doesn't change the capabilities of the Turing machine. All right? And finally, I can say something after an entire semester course that's allegedly about computers. I can finally give you something like a punchline. What this means, what I just wrote there, if you believe me, it means that your real actual computer is basically the same as a Turing machine. You can think of your computer, it doesn't have a tape, it has a hard drive or some kind of, flash memory or something. Your hard drive is not really arranged like a tape. It's not a long, straight thing. A real hard drive is kind of round, but it works just like a tape. And your computer accesses parts of the memory one by one. And so your computer is acting like a head. Now, it doesn't have to move one spot to the left or right in every step. It can jump around in the memory. But anyway, all of these things are equivalent to Turing machines. So a real-world computer is, I will say, abstractly at least, equivalent to a Turing machine. Equivalent. Right? Abstractly equivalent, I mean, it has the same theoretical abilities as a Turing machine does. All right? The tape, your computer uses its own memory, its hard drive or whatever, as if it were a tape. Also, your computer has other sources of data, like the internet is you can imagine the internet is like a giant tape that your computer can access at any time. And your computer also gathers input from things like the keyboard and the mouse. You can think of those as like a tape also, because those are also sources of information that the computer can access, or things like, you know, your camera or the Wi-Fi or something. All right, all of these things are equivalent to Turing machines. So when we discuss the various capabilities of a Turing machine, we are really also talking about the capabilities of our own electronic computers. And the fact that, this should surprise you, I know it's time to go, but the fact that there are things out here, these are things which cannot be computed by Turing machines. What this means, if you really believe me, is that there are certain types of things which cannot be computed by real-world computers. And it's true, there are such things. There are even functions, you know, rather than saying this in terms of languages, there are functions like mathematical functions, which I can actually show you the definition of, that no computer can compute the answers. It's a true fact. Very strange. That's where we're going for the next week and a half, though. All right, that's all for today. Thank you for your attention. Have a good weekend. Do that homework.
And achievements.
See you later.
Those functions that you're talking about?
No, not really.
What
I
are
mean,
the functions?
well, it's hard to explain.
Oh.
they're not things that I can say the definitions of.